Hello everyone, welcome to topic 2.7, VSPER and bond hybridization. In this set of notes, we will look at how VSPER theory uses Coulombic repulsion between electrons as a basis for predicting the arrangement of electron pairs around a central atom. And that both Lewis diagrams and VSPER theory are useful for predicting the electronic and structural properties of many covalently bonded molecules and polyatomics, including molecular geometry, bond angles, relative bond energies, and based on bond order, bond lengths, presence of a dipole moment, and a hybridization of valence orbitals of the molecule. So just as a heads up, the presence of a dipole moment means polarity, whether or not a molecule is polar, and the structure and VSPER theory are useful for that. And then finally, the terms hybridization and hybrid atomic orbital are used to describe the arrangement of electrons around a central atom. When the central atom is sp hybridized, its ideal bond angles are 180 sp2, 120 sp3 is 109.5, but these will vary depending on the presence of lone pair electrons. Okay. So let's get started. Molecular structure, the VSPER model. The valence electron share repulsion theory, or VSPER theory, predicts the geometries of molecules and polyatomic ions. The shape or geometry of a molecule is determined by lone pairs or bonds on the central atom of a molecule. As these are areas of electron density or charge clouds, and they want to minimize electron-electron repulsion by positioning themselves as far apart as possible. Lone pair electrons repel more than bonds and tend to compress the angle between atoms. That makes the angle smaller between the bonding atoms if there's a lone pair present on the central atom. So some steps to determine the geometry. Obviously, first you need to draw the Lewis structure. As a hint, hydrogens are always on the outside, they are not in the middle. Then you need to count the bonds and lone pairs around the central atom. Okay? Lone pairs and bonds are charge clouds, and these allow and help take the shape. Once you know these, you can keep going. Then you use the arrangement of the lone pairs and bonds, and how many you have, to determine the molecular geometry from the chart provided. You need to memorize them, okay? And we'll do a lot of practice with this. So you need to memorize the geometries and the bond angles, because the charts are not provided. If there's more than one central atom, we determine the geometric shape of each central atom individually by following the same steps as listed above. Okay, so here are some of these. So there's a few different pictures of these. That's why this section is so long. So you need to memorize these, okay? And so here it lists like charge clouds, and this kind of is what I would look at, is how many electron groups or charge clouds do I have, right? And then from there determine, are there lone pairs, and how does that lone pair presence determine the shape? Okay, so trigonal planar, there's 3 charge clouds, and they're all atoms, so it's a flat triangle. However, if I replace one with a lone pair, it becomes bent. If I replace 2, which is not shown, it's linear, because 2 dots or 2 atoms connected by one bond makes a straight line. You can't bend a bond. You can bend around an atom with multiple bonds, which is what VSPER theory is, but you can't bend a bond. Same idea here. The 4 group is generally tetrahedral because it's got 4 points and it's a hedron or a shape, tetrahedral. However, if I replace one with a lone pair, these are still 3-dimensional because that lone pair pushes down on those bonds. But it's a triangle pyramid, right? Pyramid means it pops up. It's not planar. It's not flat. It's a pyramid because it has that lone pair. And then if we replace the second one, it is now bent because those could be linear if those lone pairs weren't there, because it's two bonding atoms off the central. But those lone pairs push and bend that line. And the same idea here. There are reasons for all of these. If we turned this one on its side, we could see that it teeter-totters. Like it could teeter-totter both directions. This one is trigonal bipyramidal because there's a triangle in the middle, and then there's two pyramids on the top and the bottom. This is T-shaped because it's a T, and this is linear because all the electrons are in the 120 angles around here in the middle, leaving the iodine atoms along the center axis. And it keeps going. Octahedral because it has 8 sides and it's a shape, so 8-sided hedron, 4 at the top, 4 on the bottom. Just because it has 6 points doesn't mean that it's 6-sided. It is 8-sided. Square pyramidal because there's a square in the middle here, and then it pops up at the top like a pyramid, so that lone pair there just hangs out. And then we have square planar because the two lone pairs keep everything flat, because you have one on the top and the bottom. Okay, and here's another way to visualize it. Not that that is super legible. Wow, your textbook also has a set of these. Okay. And then here we have it listing based off of how many bonding or how many groups of electrons, and then what happens when we replace one of those groups and it's no longer a bond but a lone pair. Okay, and the corresponding angles. The big thing you need to pay attention to is what the angle is if all of them are bonded, and then what happens when you add lone pairs. That bonding angle becomes smaller as you add more lone pairs. And that's really all you have to remember. Okay, continuing on, we have bond hybridization. Okay, so when atoms bond, their non-bonding orbitals, the orbitals that we did with electron configuration, they hybridize with each other and create bonding orbitals that are like a blend of the atomic orbitals that we discussed with electron configuration. Okay, so to explain molecular geometries, we assume that the atomic orbitals on an atom mix to form hybrid orbitals. These are our bonding orbitals. The atomic orbitals hybridize when they bond. The shape of a hybrid orbital is a mix of the shape of the original atomic orbitals. Okay, so S spherical and P dumbbell, those kind of blend and become a new bonding orbital. Okay, the total number of the atomic orbitals on an atom remains constant, so the number of hybrid orbitals on an atom equals the number of atomic orbitals that are mixed. So in methane, which is CH4, the 2s and the 3 2p's, because there's 4 bonds, right? So I could draw that out. So valence electrons is what you bond with. So we have our 2s and our 2p, and this is the valence orbital diagram for carbon. Okay. These, we know that when methane forms, we have this. So it has 4 bonds. So that means that carbon, because it's bonding 4 times, has to use 4 atomic orbitals to bond. So those, all 4 of those orbitals, the 1 2s and the 3 2p orbitals, are going to hybridize and form the sp3, and there's 4 of them, bonding orbitals or hybrid orbitals. Okay, so in general, the sum of the superscripts, so here we have S1P3, that tells me that this is 4 bonds, okay, or 4 bonding regions, bonding domains, okay, or not just bonding, but electron clouds. It's up here, because lone pairs will occupy a bonding or a hybrid orbital. So the sum of superscripts in the methane equals 4. So you need to be able to identify SP, SP2, and SP3 hybridization in AP Chemistry. So what that means is that these ones here are tested. These are exception rules, and they would give it to you. They would tell you, hey, this is what the hybridization is. You may need to use it. To explain a pattern or a trend. Okay, so it's an exception. You are not going to be expected to be able to identify them, but you may be given it and say, hey, how does that fit here? Okay, but that's like a very, very small exception rule that might not appear on the test. Okay, but you do need to know SP through SP3 for the assessment. Okay, so overlapping orbitals from for single bonds, or for the first bond, whoa, I went too far, are known as sigma bonds. Okay, sigma single. Double and triple bonds are formed by unhybridized p orbitals and are called pi bonds. P orbitals, pi bonds. So double bonds contain one sigma and one pi bond. So you have a bond, and this isn't something that you're expected to be able to draw or know, but you have a bond going across between two atoms of overlapping orbitals, right? So those are overlapping orbitals. But then you also have a pi bond. So p orbital, and these overlap to form that double bond. And then you would have another for a triple, and these always form on that XY axis, XYZ axis, where you have Z, X, well, Y and X axes. Okay. So, moving forward, the sigma bond is 1 sigma and 2 pi. So you don't need to be able to draw that on that I drew there, but just to kind of give you an idea that a hybrid orbital is always the sigma bond, and that always forms whenever something bonds. But if we have a double or a triple bond, the additional bonds after that first bond, so a double, it has 1 pi bond from overlapping p orbitals. Triple bonds have 2 pi bonds from overlapping p orbitals. Okay, so then we have bond strength and energy. So as the number of pi bonds between two atoms increases, the bond increases in strength and energy, but it decreases in length. So it becomes, as you go from a single to a double to a triple, you increase the strength and energy needed to break that bond. So the strength of the bond and the energy you require to break the bond. However, it becomes shorter, like much closer together. So pi bonds present in double and triple bonds pull the atoms closer together. Triple bonds are the closest and shortest bonds with the highest energy required to break them, while single bonds are the longest and weakest with the lowest required energy to break. Double bonds are stronger and shorter and higher in energy than single bonds. Bond order is basically assigning a number to the type of bond that's associated with it. We saw this in section 2.6 when we were looking at resonance and how that averages, and we had an example where it was a bond order of 1.5 or 1.5 bonds because it was averaging, the double bond averaging between two locations. Well, here the bond order is the number of bonds between two atoms. When the bond order increases, the bond length decreases and energy increases. So that means that the energy increases, or length increases, and energy increases this way. Oops, T-H-E-N-E-R-G-Y. Okay. So for a molecule that exhibits resonance, we can see that bonds that have resonance are experimentally determined to be the same length. So if we can swap that double bond, as we see in ozone, between two spots, we actually see that in this one, this bond area and this bond area, like, because these will actually have resonance, they actually have the same length, and it then has a bond order of 1.5, averaging between a double and a single bond. Like 1 plus 2 is 3, and we have 2 bonds, or 2 bonding areas. So we have 3 bonds total, 2 from the double, 1 from the single, and we have 2 atoms that this central oxygen can share it with. So that means we have a bond order of 1.5. In the nitrate ion, we see that there are 4 bonds, right? 4, 1, 2, 3, 4, shared between 3 atoms, and 3 atoms of oxygen and the 1 nitrogen. So that means our bond order is 4/3, or 1 1/3. Okay, also adding on to this is bond polarity, because these are all tied into Lewis structures and the VSPER theory. Like, we use all of these with it. So when electrons are shared in a covalent bond, the shared electrons spend more time around the more electronegative element. This gives the more electronegative element a partial negative charge, and the less electronegative element a slightly positive charge. This can result in a polar molecule if those dipoles in the bonds don't cancel out. The arrow in the diagram here points to the more electronegative atom and where the electrons tend to spend more time. Hydrochloric acid, or hydrogen chloride, depending on the state of matter it's in, is a polar molecule because there is a dipole moment that doesn't cancel out. So if a molecule is polar, it has a dipole moment. Okay? That means that the dipole moments of each bond sum together to point in a general direction that the electrons are all going to travel. They are going in opposite directions to cancel each other out. So if a molecule is polar, you will need to know if the bonds are polar and the overall shape. Okay? So in this example, we see that carbon dioxide is linear. Generally, if it has a lot of symmetry, so like you spin the carbon dioxide around, it all looks the same, it's probably not going to be polar. Okay? So when we draw these arrows pointing to the more electronegative element, they go in equal and opposite directions. And this demonstrates that the molecule has polar bonds, but is overall nonpolar. Example B shows the water molecule. Because the molecular geometry is bent, so it lacks some symmetry, the arrows point in a general direction that the electrons will travel toward. So we end up with a positive end and a negative end. Okay, so that tells us that the water is a polar molecule. Okay, so now we're going to do some practice with this. Whoop, whoop. So determine the molecular geometry and predict the bond angles for the following. So ICl2 ion. So we draw the Lewis structure, because that's how we have to figure out geometry. So drawing the Lewis structure means we have to figure out valence electrons. So the iodine plus 2 chlorines plus 1 from the charge, because it's got a -1 charge here. Okay, and so you're left with 22 electrons. So then we draw them, so we have I bonded to chlorine, keep it symmetrical, okay? So we used 4, and so we have 18 left. So 2, 4, 6, 8, 10, 12, 14, 16, and iodine is in period 5, so it can do an expanded octet, so I'll put those last two there. Brackets for 1-. Everybody's got an octet or more, iodine over 8, but that's okay because it's allowed to. So we look at this and we see that it has 5 groups, which puts it in the trigonal bipyramidal group. Okay, but these are lone pairs because this is a 120-degree angle, so that puts the electrons farthest apart. So our atoms are here, and we see that they are in a straight line, so that geometry is linear. And so the bond angle between the atoms should be 180 degrees. That's what it usually wants to know when we have an angle, bond angle request, the angle between all the bonds. It doesn't care about the lone pairs. Next we have SOF4. So we have sulfur plus oxygen plus 4 fluorine is 40 electrons total. So drawing S, and then we have 5 bonded to it, so that tells me it is probably trigonal or bipyramidal, but we'll check. So oxygen, fluorine, and it doesn't matter where you put the oxygen, just that it is on there. Okay, so you use 10 to bond those, so now we'll add 30 electrons around here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. Did I count that right? Oh no. Okay, counting again. 8 times 5 is 40, so we're at our total that we're allowed on our molecule. Well, if you remember from earlier, the formal charge for sulfur needs to be as close to 0 as possible. Well, here 6 valence electrons minus 5 bonds is a positive 1, and for oxygen, so the formal charge for oxygen, this is sulfur, is 6 valence electrons minus 1 bond plus 6 lone pair. That's a -1. But if we double bond this here, we see that this drops to 0 because this goes up and this goes down, and then this becomes 6 bonds, and so these are both now 0. So I got them both to 0 by forming that double bond. So now this is my completed structure because everything's at a 0 formal charge. You can check fluorine yourself. So now I can determine it. Well, it looks like it's got the same thing, but it has atoms on all of these, right? So that means that this is trigonal bipyramidal, and that the angle between all of the fluorines here is 120 because there's 3 of them in a circle, so 120 degrees, and then from our axis here to the circle fluorines, it's 90 degrees. So those are the different bond angles there. Okay, another example. Draw the Lewis structure for the following chemical species and indicate the hybridization on the central atom and the total number of sigma and pi bonds in the molecule. So, well, hold on. Count, so 4 plus 5 plus 1 from the negative charge is a total of 10 electrons. Carbon is central, and it bonds to nitrogen, so we use 2, so we have 8 left. 1, 2, 3, 4, 5, 6, 7, 8. Carbon does not have an octet, so we pull in and form additional bonds until it has an octet. We put brackets in the charge because that is standard notation for ions. Now we can see we have 2 regions of electrons, 2 electron clouds or domains. So that means we're going to have an S and a P. hybridization, because when carbon is working with nitrogen, it's just going to use the S and 1p to form its hybrid orbitals. The other two, these two, are going to be pi bonds, so sigma and pi. Okay, so S, in the bonds, it's using 1 sigma orbital and 2 pi orbitals. Now, carbon is considered to be central because it is the less electronegative, so we would reference it, but it actually doesn't matter here because nitrogen is the same. Okay, so if we look at our next one, we need to determine its structures. So 2 hydrogens, a carbon, and oxygen gives us 12 electrons to work with. So carbon is central, and it bonds to oxygen and the hydrogens. Then we distribute electrons, and we see that carbon needs to share a pair with oxygen in order to have a complete octet. So when we look at this, carbon has 1, 2, 3 groups, so it is going to use 3 orbitals. So that means it has sp2 hybridization. And then it has a single bond here, a sigma bond here, and a sigma bond here, so 3 sigmas. And then that double bond brings in 1 pi bond for that compound. Okay, our next example, scroll. Well, that's fine. Okay, is ammonia polar or nonpolar, using the molecular shape and polar bonds, and indicate if the dipoles cancel using arrows. So again, draw the molecule. So 5 plus 3 hydrogens is 8. So ammonia. Well, we see here that this is trigonal pyramidal, so we need to draw it like that, because that'll show us that the H and N bond is polar, with nitrogen being more electronegative. So all of these arrows are going to point towards nitrogen. That means that we have a general dipole going towards nitrogen with a positive and a negative end. And then we have the lone pair, which also adds to that negative component and breaks symmetry, allowing this molecule to be polar. Okay, and so this, because it is trigonal pyramidal, it lacks symmetry and allows it to be polar. And then bonds are polar. And add up for a dipole moment. Okay, so then now we have our next example. Consider the Lewis structures for ethane and ethene below. The carbon-carbon bond in which molecule has the highest bond order. So we look at this, and this is a double bond which has a bond order of 2, and this is single, so that is a bond order of 1. So that would be the C double bond C in ethene. E-N-E, sorry, has a bond order of 2. And then which one has the lowest bond energy? Well, that would be the one with the fewest bonds, so that would be ethane. Because that is the weakest. Single bonds are weaker than double bonds, which are weaker than triple. Okay, so now here's our we do. Okay, for A, pause the video. Actually, for all of this, pause the video, work it out on your own, and then resume the video for the answers in the walkthrough. Okay, so for the first one, we should see that we have linear for both of these with a bond angle of 180 degrees. We then can use that for B and see that both of these are SP hybridized, so the hybridization does not change, and we get that from the Lewis structures. Then for C, we're going to use this molecule to answer the questions. So looking at the hybridizations, we see that carbon 1 has 4 bonds, so that is sp3 hybridized, adding the superscripts. 2 is sp2 hybridized, 3 is sp2 hybridized, and then 4 and 5 are both sp hybridized. When we look at the bond angles for A1, since there are 4 groups, that is consistent with tetrahedral electron geometry, and that is a bond angle of 109.5 degrees. A2 is trigonal planar, and that is a bond angle of 120 degrees, and then the A3 is linear, which is 180 degrees. Counting all the bonds in there should give you a sigma bond count, which is 10, and then counting the double and triple bonds, you should see 3 pi bonds. So that concludes these notes. Complete the you do and check your work. Thank you.